same time. Okay? Now each team has, again, 20 minutes to report your project. And you are supposed to report your project using the slides one more time. And in order not to confuse you, I think let me clarify the following. Okay, you have to submit and upload. The e-files for both, okay, for both. And I don't want to confuse you, but someone came to me and asked about this. The slides and your paper. Okay, so this is kind of full report. And also, upload the 10 files. Okay, so upload the e-files, the electronic files for both your slides. That's for the presentation, oral presentation, for oral presentation. Okay, and also the paper. And please submit all again the top slides and the paper. Okay, again, I will open the link for this upload. And please submit your slides and paper right before your presentation. Okay, got it? Okay, so this is right before presentation. Okay? I think that's clear, so that you won't be confused, all right? Originally, I don't want to waste your paper writing this meeting, but I think that confused many of you, so make it straight. Upload your e-files for both the slides and your paper, electronic files, PDF or PowerPoint, but I prefer PDF, okay? And also, print out, okay, this means you have to print out your slides and paper, and give me your slides and paper right before the presentation, so I can take a look at your slides and presentation, okay, and your papers. Okay? Right there, I will announce this again using the platform. Okay? Now, a couple of you, a very few of you, almost did not submit any homework assignment. That's a big problem. That is a big problem, okay? Now, in case your report, your template is not so good, in some sense, you may have a problem, okay? Some of you almost did not submit any homework assignment, did not give me any homework assignment. It's not a good sign. It is not a good sign, okay? So, what I'm saying is, you have to do your term project. You have to do your term project very well. You have to try very hard. Otherwise, you may have a problem. Okay? All right? Any question? Okay. All right. Let's start our lecture. Resume the lecture. Okay, we should finish the chapter 8 today. Okay, to save the time, I have already uploaded the chapter 8 with supplement, so if you want, you can open the slides. Okay, so that will speed up the process. Okay, let me recap a little bit very quickly. Now here we model the sampling process as an impulse train. So this impulse train, okay, this one. This impulse train is used to model the sampling process. Okay, what do I mean by that? That means, look at this figure here. Suppose I have a continuous signal XLP. Okay, we have a continuous signal XLP and go through the sampling process. So go through the sampling. So we have XLP which is continuous. And after the sampling, this is the result. After the sampling, we have the sampled signal. These are the sampled signal at any sampling instant. Okay, now each, be careful here, each of this magnitude actually goes through infinity. But the area of, remember that the area of the delta point is 1. So suppose this is the sample signal. Okay, then we call this the n is the s. So this is x of n e the s times the delta function. So this function value goes to infinity, but if you integrate, this function, now this is the sample signal, so we can have an NPS sampling instance. So this can be written as x of NPS times the integration of the delta function, shifted delta function. Okay, now remember that the area of each delta function is equal to 1. Okay, so this becomes x of NPS. So don't be fooled. Please do not be fooled or be confused by this arrow. Okay, this arrow means the function value goes to infinity because it's multiplied by the delta function. But if you integrate this function, okay, at NTS, is equal to x of NTS. That's it. Okay? So be careful. Be careful. Why we do this? This was invented by someone. I mean, I don't know. That's for the. Later on, we are going to see this. That's for the zero over whole. It gives a very good mathematical explanation. So by using this impulse train, we are able to treat discrete signal as continuous signal. That's a tricky part. Okay? All right. Anyway. So mathematically, the sample signal x of s of p, okay, that's this one. This is x of s of p after the sample, the signal over here, or the one that I showed you. This one, this is x of s of p. Can be written as the product of continuous signal x of p times the impulse train. Okay, this is the impulse train. Times the impulse train. Delta sub t sub s of p. Okay, so it is an impulse train. There's multiple impulses. And since this impulse train is a periodic function, it repeats every t sub s second. Okay, so this is a periodic function with period. T sub s. So T sub s is a period. Now, since it is a periodic function, so we are able to write it as a Fourier series. Okay? And the coefficient in front of the function, complex exponential function, one of which is retained by using the projection. In this one, next page here. And this coefficient is equal to it is equal to the projection, okay? And this is the definition for the Fourier projection. The mean value of the inner product of the function we are going to approximate times e to the negative k omega s times t. That's the Fourier series. That is the Fourier series. And actually, it is based on the projection. We have mentioned this in the previous chapter. It turns out that the coefficient is only 1 over T sub s, very simple. Okay? So I can replace this function by this Fourier series expansion. Okay? So the sample signal x of s of t now can be written as 1 over ts times AU. We bring this x of t into the summation. You multiply this entire impulse track by x of t. And now you can see that this is the index for n. X of t is no index n here, so we can move this into the summation. Okay? Replace the impulse track by the Fourier series extension. So x of s of t now can be written as a Fourier series extension like this. Sort of, okay? Fourier series extension. Alright, so far so good, just on mathematical manipulations. Now, a big issue is the following. Again, in the previous page, we have the sample signal x of s of t. Now, in your mind, you have to remind yourself what is x of s of t again. This one, and this one, or this one, and then this one, or this sample. Okay, this can be written as a Fourier series expansion, 1 over ts times as I mentioned. Okay, now if we take the Fourier transform of this function, the infinite series, okay, then we have omega x of s of omega. That is the Fourier transform. Or sometimes I prefer to call it frequency response. Frequency response is equal to 1 over ts, which is a constant, times the summation of the term x, capital X, okay, capital X of x, capital X of omega minus a times omega s. That is because, by definition, this x of omega, that is the Fourier transform of x of t, the original Fourier transform of x of t. And since each x of t is multiplied by this exponential function, complex exponential function, and that is the time delay, sort of. So in the frequency domain, this is the frequency shift, a times omega s, this shift. Okay? We will call this modulation, right, in the previous chapter. So the okay, then I show you this one here. So the Fourier transform, and we can enlarge this. The Fourier transform of this term, this term, is equal to the integral of x of t times e to the j omega sub 0 times t minus j omega t in this one. I call this omega 0, okay, this is a notation problem. I call this omega 0, sorry. I did not change that. I should change that as well. Okay, so for the moment, you can call this k times omega s, the omega 0. Okay, just for location of convenience. Maybe we need to correct that next time. Okay, so this function times the e to the j omega t as a Fourier transform. And now we can define these two complex exponential functions. Okay, and then use the definition of the Fourier transform again. This time. Here. Okay. That is indeed the Fourier transform of x of t, but with a frequency shift omega sub 0. Okay? Now this omega sub 0 in this case is k times omega sub s. The omega sub s is the sampling frequency. 2 pi times over ts. Ts is the sampling time. Okay, what is the sampling time again? The time between samples. Okay, so this is the sampling time. What is sampling time? 2 sampling time, 3 sampling time, and so on and so on. Okay, what is the result? Tells us. What does the result tell us? Okay, it tells us, suppose I have a frequency response of the original signal. So this is the original signal. This one? I'm sorry. This one? This is the original signal. And then suppose it has a frequency response this way. Now, after the sampling, in the mathematical model, we model the sampling as the impulse strength. So we multiply x of t by the impulse strength, right? This is in the time domain. So in the frequency domain, it becomes the convolution of these two frequency responses. Now we also can prove that very, very quickly, but it's been done before. So of course we can do it again with a question. Come to me. Okay, the frequency response or the Fourier transform of this impulse strength turns out to be also an impulse strength like this. Okay, very interesting. So in the frequency domain, we convolute these two frequency responses, and eventually we come up with the frequency response of the sampled signal. So this is the sampled signal in the time domain, this one. And is the associated frequency response is this one. So we can see that after the sampling, this is in the time domain. After the sampling, the frequency response now were duplicated. Okay, these are due to the sampling. And this is a very, very important result. So you have learned many stuff. You may forget some other stuff. That's fine. But this one, you have to keep that in mind. Okay? For digital signal, for sampling process. Again, repeat that again. This figure is very important. The continuous signal has the impulse response, has the frequency response. Okay? And then after the sampling, this is the sample signal in the time domain. The frequency response will be reproduced, will be regenerated at every sampling instant. Okay, so this is the original. And then for one omega s, for one sampling frequency, it reproduced the frequency response. At 2 omega s, it reproduced another frequency response. At -1 omega s, it reproduced one sampling frequency. One frequency response. At 2, this is -2 omega s, -2 times the sampling frequency. It also reproduced the frequency response. Okay? Again, these are due to the sampling. And because of this, we have a very big issue we have to consider. How do we choose the correct or right sampling time TS? Okay? Again, how do we choose a proper TS? And I'm going to fix this one here. So the sample signal is this guy. Okay, now we read as Fourier transform like this, Fourier series. Okay, and then we take the Fourier transform. We have the frequency response. So it's a summation of all the shifted frequency response of the original signal. Okay? And also can be considered in this way. Okay? That's another approach, but they are the same eventually. This sample signal x of t can be written as summation x of ATS times impulse strength. Okay? Originally, it's a product of the continuous signal x of t times the impulse strength. Okay? This is a continuous signal. And this is the impulse strength. Okay? But then we can write the impulse strength in this way, t minus nts. N can be from negative infinity to positive infinity. But if we consider only total signal, then we start from zero. Okay, but here, let's consider an arbitrary case. Now, since this is the index for n, and x of t is no index, so we can move x of t into this dimension. Okay, now again, go back to the impulse strength. This is 0, this is 1 ts, this is 2 ts. 3ts. It has function value only at the multiple of the sampling instant, NTS. So this also can be written as the summation of x of NTS times the build-up point with the shift. Okay? So that's fine. Because all the function value in between the sampling instant is 0. For the impulse strength. So that's why I can replace x of t by x of nts. Alright, now if I take the Fourier transform of this guy, okay, directly, I have the frequency response of the sample signal equals, and this is a constant, okay, times x of nts times the Fourier transform of the build-up function. That's a shift, right? That is a shift. E to the negative j omega ts times n. Then if I call this tau time delay, and this nts as a time delay tau. And in the frequency domain becomes this. Okay, so these are just some fundamental stuff we have to know. Again, the important thing is this figure. Okay? This is the most important stuff you have to know. Alright, so let's go to the next page. Okay? So how do I determine the correct sampling frequency? If we use this figure to illustrate the concept, that will be the following. If this is the frequency response of the signal, of the continuous signal, and after the sampling, we have the frequency response for the sample of the signal. Okay, there's a subscript S here, means it is the sample signal. In order to reconstruct the signal, the sampling frequency must be greater than or equals to 2 times omega max. Okay, so again, let me use the chalkboard here. Okay, this is omega s. Okay. This is omega s minus omega s. Okay, let's go that again. Okay, so this guy is the original frequency response. This one. And after the sampling, the sample signal regenerate or introduce some additional frequency response at every sampling frequency. Suppose there is a maximum frequency for the frequency response, x of omega. Okay? So this width is the omega max. So for the second frequency response at omega s. Okay, and this one is the leftmost frequency response reproduced at omega s at the one sampling time. So this is equal to omega s minus omega max. In order not to have an overlap, okay, this point should not collide with this point. So omega s minus omega max supposed to be bigger than omega max. Okay, or the sampling frequency must be bigger than 2 times omega max. Okay, I think that's easy to see that bigger, right? So this is the basic requirement we need to bear in mind. In order to have no aliasing phenomena, we need to ask our sampling process to satisfy this constraint. But the sampling frequency in omega s, this is equal to 2 pi over t. Omega s is 2 pi over t, must be bigger than 2 times omega max. Omega max is the maximum frequency of the frequency response of the continuous signal. The omega is 2 pi over the sampling time ps. Okay? All right. What happened? Let's see. You can see that. Suppose I have a continuous signal x of t. Actually, that's a sinc function squared. Okay? The frequency is 5 pi. And this is the frequency response, triangle. Okay, now if we sample right at 10 hertz, okay, so this is the sample signal. These are sample signals. And then the corresponding frequency response is given by the right hand side. So all the frequency response of the sample signal are given by the shaded area of the triangle. So at every one sampling frequency, the sampling frequency, the frequency response is reproduced. Okay? Now since this is exactly equals to 2 times omega max, so we can see that there's no overlap. Just right next to each other, no overlap. So theoretically, we can have a perfect reconstruction. Okay, we will see that later. Okay? And if we use even the faster sampling, 20 hertz, okay? So that means we take samples even more. and we sample the signal even faster, 2 times faster than the previous one. Then this is the sample. This is the frequency response of the sample signal. We can see that widely, and no overlap at all. No overlap at all. But if we reduce the sampling process, okay, the sample rate now reduced to 5 Hertz, then we have the sample signal at those points. The corresponding frequency response, now you can see that, has very severe overlap, okay, and then we call this deviation. That means we are not able to reconstruct the signal using those discrete signals. Okay. Okay, here is a quick example. Yeah, those are the requirements we just mentioned. Suppose I have a continuous signal x of t equals 2 times cosine of 2 pi t plus 1/4 t. Here we let t between negative infinity to positive infinity. So basically it's a non-polar signal. That's fine. Now first one, if t sub s is 0.4 second, okay, so the corresponding sampling frequency omega sub s is 5 pi. And this 5 pi is bigger than 2 times omega max. Okay, omega max here is 2 pi because it has only one frequency component. So omega max is equal to 2 pi. So 2 omega max is 4 pi. So our sampling frequency 5 pi is greater than 4 pi. So that is it satisfies the Nyquist here. Nyquist criteria. What is Nyquist criteria? Or Nyquist condition? Or Nyquist criteria. Okay, and after the sampling, the sample signal is of NTS. It can be written as 2 times cosine 2 pi. 2 times cosine 2 pi times 0.4 n because we replace t by n here. Okay, the x of t is 2 times cosine of 2 pi times t and plus the base 1/4 pi, right? So this means the omega or omega max is 2 pi. Now if the sampling time is 0.4 seconds, then the x of nts is 2 times cosine of 2 pi times n times ts is 0.4. Then plus the base 1/4 pi. Okay, and then 2 pi times 0.4 times n plus 2 pi. Okay. Plus n 4 pi over pi 450 times pi times n. So this is direct substitution. So this is a discrete signal at every instant. 2 times cosine of 4/5 pi times n plus 1/4 pi. Okay, and here another one is t sub s is 1 second. Now this time the sampling frequency is 2 pi only, so which is smaller than the required sampling frequency. The minimum one is 4 pi. So you can predict there will be an aliasing. What does that supposed to mean? Now look at the following figure here. In the part A, this figure, the sampling time is 0.2 seconds. Okay, 7 times 0.2 seconds. So it satisfies the Nyquist condition or Nyquist criteria. Okay, So that means we can reconstruct the continuous signal by using the discrete signal. And then in the second case, TSMS is 0.4. That's the one we received here. 0.4, this one. Okay, so you can see that these are the discrete signals. Okay, theoretically, it satisfies the Nyquist criteria or Nyquist condition. Okay, so keep that in mind first. And then for the part C, the sampling time increased to 0.5. Increased to 0.5 seconds. Okay? So this is right. Okay, so 0.5 for that. TSMS is 0.5. So which means the omega is 2 pi over 0.5. That's 4 pi. Right? So which is exactly equal to 2 times omega max. So right equal to 2 times the maximum omega. Okay? Again, theoretically, we can reconstruct the signal. But if you look at the discrete signal, the magnitude of the sample. Okay? So actually there's a problem if you want to use those signals to reconstruct the groove lines, the original continuous signal. You will see there is a problem. Okay? So this is not a good idea to use exactly equals to 2 times the maximum, 2 times the maximum frequency of the signal. It's not a good idea. Now, if you use even larger sampling time, one second. Okay, so you can see that what do you have? Constant sample signal. You cannot see any oscillation from the sample signal, right? So that's a big issue here. You lose the information of the continuous signal. Okay? It's not a good idea. Very bad idea to say that. Okay? Now, here is a question for you. Think about this. Very interesting. In the case A, in the first figure, case A, the sampling time Ts is 0.5. Okay, here at mod n equals 5 means every 5 signals. Okay, go back to the first cycle here. And 5 times 0.5 is T sub 0 is 1 second. So the period for this case is 1 second. 5 times 0.5 plus 3. Okay, and count it 1, 2, 3, 4, 5. Next one, start from the first signal again. So the period in discrete is 5. In discrete time is 5. Okay, but in continuous time you can see that 5 times 0.2 equals 1 second. Okay? And this is the same as the original signal. For the second, for the third one, jump to this one. N equals 2. Okay? The part C, the sampling time is 0.5 seconds. So 0.5 times 2 equals 1 second again. Okay? So this one, even though it looks weird, like I mentioned, we may lose information. But does not change the period of the signal. However, if you look at this one, okay, this one is satisfied, and this is 0.4 seconds. It satisfies the Nyquist criteria, but what is the period here? Now let's count it. How many sample signals do we need to go back to the first one? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay? So n is 5. So every 5 samples, it repeats again. But each sampling time is 0.4 seconds. 0.4 seconds. So this makes the period be 2 seconds. You can see that. Every 2 seconds. Every 2 seconds. The signal repeat again. Why? Here we do not change, we do not violate the Nyquist criteria. But how come the sample signal change the period of the signal? Think about this, what happened? Think about this, what happened? EJ, are you okay? Are you okay? Where are you? You are wandering in the air somewhere, I don't know. Are you okay? Don't worry, okay? I mean, are you okay now? Okay, so think about this. Why, for this case, it's very interesting. It does not violate the Nyquist condition. However, it does change the period. The sample signal does change the period. The period becomes 2 seconds. Okay? But the period for the original continuous signal is 1 second. Okay? What happened here? Think about this. Okay, now look at this figure. It's also very interesting. Okay? Now, here we have 2 continuous sinusoidal signals. This one, that's 1 hertz. Okay? This one, frequency is 1 hertz. And the solid one, the frequency is 6 hertz. 6 hertz. 6. Okay? Now, if we sample the signal at 5 hertz, means we take 5 samples from 1 second. Okay, in a 1 second interval, we take 5 samples. And you can see that just by looking at those samples, you cannot tell the difference whether the samples are taken from the 1 frequency, 1 hertz signal or the 6 hertz signal. So this is also an alias. Okay, and why this happened? Get a spectrum. And it is the frequency hertz. And then we have 2 hertz. This is there. And our sampling frequency is 5 hertz. This is the sampling frequency, 5 hertz. Yeah, 5 hertz, 1 hertz. Alright, so our signal is 1 hertz. So in a spectrum, we can see that there is a component at 1 hertz and also negative 1 hertz as well. Very asymmetric. We can see the magnitude. And it's considered now, due to the sampling at 5 hertz, and this is the sampling frequency omega equals 5 hertz, then we reproduce the frequency response at 4 hertz and 6 hertz. Okay, that's the F1 equals 5 hertz. First signal. Then what about the second signal? Alright, so this is the sampling frequency. Our signal is 6 hertz. So we have to do 6 hertz. So which means we are going to see the frequency component here, 6 and negative 6. But we use the sampling frequency 5 hertz is under the required bandwidth frequency. Okay, so we are going to see okay, let's take a break. Let me withdraw that because the scale looks different, so I'm confused. Okay, let me withdraw this next one. Okay. So that they have the same scale. Okay, you can take a break. That's fine. And let me finish this. So there's one component at 6 hertz. And there's another one at negative 6 hertz. Okay. Then, due to the sampling, In the first figure, that is the power spectrum of the sample signal for the first continuous signal. The frequency is 1 Hz. Okay, slower. Now, since the sample frequency is at 5 Hz, so the complete sample signal, the power spectrum is the following. Okay, the frequency is 1 Hz. That's the power spectrum of the original signal at 1 and negative, both positive and negative frequency. But after sampling, the sampling frequency is 5 Hz. So at each sampling frequency, it will reproduce the frequency response. So at 6 Hz and 4 Hz, we will see the two frequency response. Okay? Again, 5 Hz, negative 5 Hz, negative 5 Hz here. This is negative 5 Hz. It will also reproduce the frequency response for the sample signal. Okay? So this is the frequency response for power spectrum of the sample signal for 1 Hz, for the slow moving 1 Hz signal. Okay? And for the 6 Hz signal, after sampling, it is not from the signal itself. The signal is at 6 Hz. So at 6 Hz, you will see a frequency response. And in the meantime, at negative 6, it also has a frequency response. Okay? So these two are the original. Okay, this one is the original. Alright, but after the sampling, say this is fs, 1 fs. It will reproduce the power spectrum of the original signal. Okay, so let's check this. 1, 2, 3, 4, 5, 6. We go back to negative. So at negative 1 Hz, you will see there's a frequency response. Okay, and also go back to the right one. 1, 2, 3, 4, 5, 6. So there's another one over there. Okay? And then for the second sampling frequency, it also reproduced the power spectrum. So let's go back to the left, 6 Hz. 1, 2, 3, 4, 5, 6. So you will see a frequency response at 4 Hz. So by using the same technology, you will be able to construct all the power spectrum or frequency response for the sample signal. Compare these two power spectrums, you can see that they look the same. They look the same. Okay? So you cannot tell the difference. This is for the 6 Hz signal, and this is for the 1 Hz signal, because they look identical. Okay? So that's because you use a very slow, I can use the word very slow. You use the sampling frequency, which is smaller than the required frequency. Okay? So this is also the aliasing This is also an AAC of the signal, right? So this is very important. One more time, you have to know what is the proper sampling frequency in order to avoid the aliasing problem, okay? Right, I'm going to turn that on. Okay. Okay, now theoretically, how do we reconstruct the continuous signal by using the sample signal? Maybe, let's see. Okay, I'll start from here. Okay, now before we take sample, actually we have to use a low pass filter to filter out those unwanted high frequency components. Okay, and this is an ideal low pass filter. The corresponding time response is the sync function like this. This is the sync function. So the output of the signal going out to the low pass filter will be emission. Okay, so this is the original signal XRP, and this is the low pass filter. The name of the emission. This is low pass filter. Okay, the impulse response is called HRP, and once the filter for the fixed on. Okay, I put this out. Okay. And the YLT is a convolution of the input signal and the low pass filter, right? Okay, but then we have to know that we also go to the sample. Then we go to the sample. So this is for this on. For the XS. This XS. Yeah, XS. Okay, here let me skip the detail, just tell you the result. Okay. So again, let's go back here. Okay, let me skip some of the details. So the impulse response of this low pass filter, HRP, is given by the sync function. Given by this sync function. This is the frequency response for the ideal low pass filter. So you can see that if we use the figure, this one. In the frequency domain, we need to run this operation of this, and this is, and we here. We got this 1/2, sorry, 1/2. Okay, so this is the frequency response for the ideal low pass filter. So it's a rectangle. Okay? Between 1/2 omega s and negative 1/2 omega s. The magnitude is equal to the TS. This should be TS. And that should be TS. Simple impact. Yes. Okay? And then the corresponding impulse response is defined by this single function. Now, after the sampling, the low pass filter, if we use single function, okay, then this impulse response is given by this guy, inverse series. It's a convolution actually, convolution of the input signal and the impulse response of the low pass filter. So it's the summation of xn, that is the simple signal, times the sinc function. Okay, now let's skip the details, sorry, I don't want to give you hard time. And let me show you the result. That's very interesting here. Okay, one more time, what is the sinc function? This is the sinc function. Okay, these are the sinc function. This is the sinc function shape. So the constructed signal will be using the sinc function. Okay, so this will be the linear combination of many sinc functions. Okay, let me show you the example. Now, this blue line, that's the original continuous signal. Blue. Okay? And the top, red top, these are the sample signal. Sample signal. And the sample frequency is 200 hertz. 200 hertz. Okay? The original signal, the frequency is 100 hertz. So right equals to the next frequency required. Now if we use those points, okay, those points, the red part, to reconstruct the continuous signal by using the sinc function, then we have this one, the purple. And you can see that not very close, not a good idea, right? Let's not construct the original signal very well. Not even close, I didn't say that. Okay, so if you use this 1, 2, 3, 4, 5, the 200 hertz signal to reconstruct the continuous signal, you have the purple one, and it's not a good reconstruction. Okay, now if we increase, we double the sampling frequency to 400 hertz. Okay, so here we have those sample signal. We increase, we double the sampling frequency. And then we use those sample signal to reconstruct the original signal by using the sinc function. Then this is a reconstructed signal. Not very close again. Okay, not very close either. Okay, so not so good. But if we increase the sampling frequency to 600 hertz, 600 hertz. So now you can see that we have those sample signal. Okay, and using the sinc function to reconstruct the signal, then we have the purple one. Now you can see that it matches the original signal much better. It matches the original signal much better, right? Okay, so the original signal is 100 hertz. The sample signal is 600 hertz, 6 times the original signal. Then we have this kind of behavior. Okay, so this is the reconstruction of the signal using the sinc function. Now I have to say that practical speaking, sinc function, this kind of method is not very popular one. Okay, it's very complicated. Not very useful, just for theoretical purpose. Okay, but to give you an idea, how do we reconstruct the original signal using the sinc function? Okay, got it? All right. Now there is a numerical example. Okay, where's that? How many names do I have? Okay, there's another good example here. So I want you to run a code, but we still have time to go through the remaining stuff. So let me finish the remaining stuff first, and then we run the program. Okay? Okay, so let's go to the next page here. Okay, now, practically speaking, how do we avoid? Yeah, I have to skip one of the another example. So let me go back to the previous. All right, this one we're saying that that's fine. Okay, now if we are considering a signal which does not have finite maximum frequency, then one of the rule of thumb is to choose the maximum frequency by using this rule. The total the total energy the required frequency, it contains about, say, 99% of the total energy. Find out that, okay? This is a rule of thumb, I just say that. By using this kind of method to determine the so-called maximum frequency of the signal. But again, let me say that one more time. The original signal does not have a finite maximum frequency. Okay, it does not have a max, omega max. You can see that it goes to infinity. Okay? But in order to have a proper sampling process, we still have to determine a proper omega max. So in this case, the omega max is determined by this rule of thumb. We choose a proper upper bound. Okay, that's the omega max we are going to use. So that the signal, okay, within the bound contains about 99% of the total energy. And then choose that as the maximum energy. And here we assume the sampling frequency is 5 omega n. So again, this is the rule of thumb. So that's why I said this method is not so practical. We just try. We try. Usually we can use 10, personally I prefer to use 10 times omega max. Okay? And we don't go through this. We just pick some proper number. Okay? Just pick some proper number, depends on your intuition. Now here for this case, the omega, x of omega is bigger than 1 over 1 plus j omega. So this is one first order system. The frequency response, this one is the magnitude in dB, and this is the phase phase in degrees. According to this computation, the omega n here is about 63.66 milliseconds about here. Okay? So hopefully this area covers about 99% of the total energy of the signal. Okay? Again, because this is a very simple function, so we can compute the number. Otherwise, it's not so easy to do that in general. So that's why I personally prefer to pick a proper omega n directly. And then choose a large enough sampling frequency. Usually I will pick 10 times omega n. Okay, so that's the issue I have to mention. And let's go back to the next one. In a practical application, suppose I have a signal XLT, and then I have to get rid of some unwanted high frequency component. So I have to go through the low pass filter first. Okay, that's H of H of omega. That is the frequency response of a low pass filter. So that low pass filter, like this one, okay, this is the ideal low pass filter, is going to cut out or attenuate those unwanted high frequency components. And then after that, we go through the sampling. Okay, so then we can use the sampling process to sample the signal. So that's a very typical process to sample signal with noise, okay, usually. Okay, this is the same as I just mentioned previously. So let me skip this. Okay, the last page here is to remind you that in the first couple of pages here, I told you that if we use the sync function to reconstruct the continuous signal, it is impractical and we seldom use it. Personally, I don't use it. Okay? Instead, we use zero overload. So again, let's start from the beginning. Suppose I have a continuous signal, XLT, and then go through the sampler. So we have the impulse, okay? Impulse, pulse, or sample signal. These are impulse, remember. Okay? But we go to the zero overload. This is a zero overload. To reconstruct the continuous signal, or piecewise continuous signal. This is the practical way we reconstruct the signal. So how do we analyze this? Okay, so let me use this one. This is my personal. So suppose I have a continuous signal. Let me put RT. The Laplace transform, or Fourier transform is not of S. And then go through the sample. We have the sample signal. And we call that R star of P, R star of P. Star means it is a sample signal. Star means it is a sample signal. And the corresponding Laplace transform is R star S. Now we use zero overload to reconstruct those continuous signals. But actually, this is a piecewise continuous signal. So how do we analyze this mathematically? Okay, zero overload is the constructed signal. This is a constant, right? In each time interval, this is a constant. The order is zero because it is a constant. So that's why it's called zero overload. Zero overload. And one more time. So this I call this alpha of t after the zero overload. Can we bring this R of 0? Okay, this is R of 0 times the rectangle signal, this small piece rectangle. Okay, so the first piece of this rectangle, this one is given by R0 times the unit step function. This 178 amperes. Right? So this gives us the first rectangle here. And then we need to get another strip, the second rectangle. So this is our P times our P minus PS minus our P minus 2PS. Then we continue this. Okay, so that's the idea. So once we have the mathematical expression, okay, these are unit step functions. I use one step U. Okay, these are unit step functions. Unit step function. And then we take the Laplace transform operations to the same. Okay, the Laplace transform of the unit step function is 1 over S. The second one is one step delayed. Okay, this is unit step function. Laplace transform of unit step function is 1 over S. You can see the total signal. Now the second one is unit step function with one step delayed. So it equals 1 over S times e to the negative t sub s times s. Okay. That's why I made this term. And the similarly for the remaining terms. Okay, now every term so now if I take that function and 0 times 1 over S minus 1 over S times e to the negative PS. Just E plus P times this is 1 over S e to the negative PS minus 1 over S e to the negative 2PS. Okay, so this can be written as, we can pick it out on the rest. 1 minus e to the negative PS. Okay, and this is the PS. 1 over S minus. And repeat the process, right? Okay, you see? So each term we can take it out. 1 over S times 1 minus e to the negative PS. So for each term we can figure out 1 over S times e to the negative PS. So eventually, every term we can figure out 1 minus e to the negative PS over S. Okay? And this can be written as from 0 times 1 of e times e to the negative PS. And of pt times e to the negative 2PS. And again, that times this 1 over S times e to the 1 times e to the negative PS. Okay, now this is important because now this laying down the foundation of integral. Okay, so each term can be factored out 1 minus e to the negative ps over s. And then times all 0, the first, second, signal. All t times e to the negative ts, all 2t times e to the negative 2ts, and so on and so forth. Okay, so this is the transfer function of the 0 loop. Surprisingly, this is the transfer function of 0 loop. Now, for the first term, the summation, built-in summation. And we can focus on this, or about omega if you want. That's equal to all 0, all p, all 2p, and okay. Now if I let so this transfer function. This is the transfer function of the solo transfer function. It's not a good word. On the 0 voltage is 0 volt. Now, if I let e to the negative ps, Vg equal to ts. The emitters times d plus all 2t times d squared, so on and so forth. Then this is the d transform of the sample signal. Okay, so this becomes the d transform. So this becomes the d transform. Yes, suppose you can see that this statement. Okay, the important thing is, for this analysis, we are able to find the transfer function, sort of transfer function of 0 to 4. Okay, the capital N, this is the and this is the impulse response. So this is the impulse response. That's the figure in the previous video. So this is the impulse response of the 0 So after the zero of the whole, all the signal becomes piecewise continuous signal like this. The staircase. Okay, I think we still have a little bit of time, so good, very good. So I need you to turn on your laptop. Oh, by the way, okay, after the signal goes through the zero of the whole, it will generate a time delay. It won't have constant time delay. Okay, so the blue line is the original signal. And the red dash, these are the signal after the zero of the whole. Okay, and the green dash, and green solid dash, these are the sort of the smooth signal for the signal after the zero of the whole. And you can see that there's a gap, and this is the delay introduced by the zero of the whole. About 1/2 sampling time, about 1/2 sampling time. Okay, and this is the analysis, quite simple analysis, okay? Because this delay is about 1/2 sampling time. So this also, this time delay, this zero also can be approximated by a first order system like this. Okay? All right, that's another story. Okay? Okay, I think we have a little bit of time, so please turn on your laptop. And I need you to run a code. Convince yourself how to construct a signal using the sync function. Simulation of sampling and then reconstruction. Okay, it's on the page 505. 505, here. 505. Okay, I think you need also the sync interpolation, sync interval. So you can have it. And also you need that's it. Okay? Try to run this one now, okay? Hopefully you can finish it very soon. So in this example, we are supposed to use the sync function to reconstruct the original signal. So let's see what happens here. So you need this sync interval. sampling. see it. Okay, keep my points. Okay, so here the f-max is 1,000. So what is the proper sampling frequency you are supposed to choose? The minimum, right? What is the minimum sampling frequency? 2 times omega max, right? See that? One more time. 2 times omega max. So the omega max is 1,000. So what is the minimum sampling frequency? 2,000. But usually we need be bigger than that. The sampling frequency. 5 times or 6 times or 10 times. Exactly equal 2 times the maximum frequency will give us a problem most of the cases. So you use 5 times. Okay, this Nyquist sampling requirement is very important, okay? So everyone, once you have learned the signal process, you have to know this is the most important guide. Okay, number 1 guide. Did you get something, gentlemen? Not yet? How about you? Okay. Your son is beautiful. signal. Because it has no particular signal. So this is a single component. This is the positive frequency. And this is the negative frequency. Negative has
All right, 5 minutes, okay? It's already late. It's already... Try to finish it if it is possible, okay? no defects, no defect, no problems. Again, I really love this, okay? I have no feeling about it now, this approach. Okay, try to clean up everything. Stop at 6:30. Okay. If you cannot finish it, I urge you to run the program at home. Okay, see what happens. It's very interesting. It's very practical and very interesting. How to use the sync interpolation to reconstruct the original signal. Something? Good. Yeah, we may need try your best next week, okay, everyone? Did you get something?